For part 2 of solving systems of linear equations, we're going to go over our second method, which is to solve systems of linear equations by substitution. We recall from part 1 that there are 3 possibilities when solving a system of equations. There's either one solution, no solution, or infinitely many solutions. So one solution, that's when we have a coordinate, an xy value as our one solution. When we have no solution and infinitely many solutions, these occur when both variables are eliminated. So that means to say that I'm working the equations and I somehow cancel out both my x and my y. So my variables are gone and I'm just left with numbers in my equation. If the resulting equation is true, then we have infinitely many solutions. If it is false, it'll have no solutions. We'll go into this further in the examples. There are several steps when using the substitution method to solve systems of equations. First would be to solve for one of the variables in either equation. The second would be to substitute that resulting expression into the other equation, the one that you didn't use yet. Solve for the remaining variable. Substitute that solution into either of the originals and check your solutions. It sounds pretty complicated right now. It actually is a little bit complicated, but the more practice you do, the easier it'll get. And we'll go through a bunch of examples to illustrate this. Our first example, x plus y is equal to 6, x minus y is equal to 2. So when we are solving systems of equations using substitution, we want to solve for one of the variables in one of the equations. So for me, I actually like to just name each of my equations because it's important that we use both of our equations. When we're choosing the equation to use and the variable to solve for, I first of all always want to work with, when using substitution, I always want to work with variables that have a coefficient of 1 because I definitely won't have to divide when solving and I won't end up with any fractions. And also, if you can avoid working with negatives, then I also suggest doing that. So for this one, I can actually use either of these equations easily. All of these variables are easy to solve for because all of them have coefficient of either 1 or -1. I'll actually try to solve for x in the second equation, just because when I solve for x, it'll move that y to the right side and it'll change to positive, right? So I'll only be working with positives. But again, any of these variables and any of these equations will be easy to work with. So while I'm working, I'm always indicating which equation I'm using. In this case, I'm using the second equation first, and I'm solving for x. So I have x minus y is equal to 2. To solve for x, I'll add y to both sides. So x is equal to either 2 plus y or y plus 2. Doesn't really matter. Okay, at this point, this equation is actually going to be very important to me. I'm going to come back to this later. And so I'm actually going to star this equation. I'm going to name this equation the star. Okay. Now is where the substitution comes in. So basically with substitution, I'm going to take whatever this x equals to y plus 2. I'm going to substitute that expression, that y plus 2, for x in the other equation. So basically I'm going to substitute y plus 2 for x in now the first equation, equation 1. Started with equation 2, substituting whatever I got into the other equation. The reason that we do this is that when I substitute this in, I'll only have one variable in my equation, and that will make it so that I can actually solve for that variable. So copying this first equation, I have x plus y is equal to 6, but now instead of x, I have the same equation, but instead of x, I'm going to be writing y plus 2. So from here, I have the equation y plus 2 within parentheses plus y is equal to 6. From here, I'll just solve this normally for y. So y plus 2 plus y is the same as 2y. Y plus y is 2y. Plus 2 is equal to 6. Solving for y, I'll subtract 2 from both sides. So I'm left with 2y is equal to 4. From there, I have y is equal to 2. So divide by 2, I'm left with y is equal to 2. That's already 1/2 of my answer. When I'm solving these, I need one x, one y. So I already have the y. What I'm going to do now is solve for x. I can do this by plugging in my answer here into either one of the originals. So I can plug it into here or here. Or, since I already did the work of solving for x, I can actually plug it into this special star equation that we talked about. So if I was to do it there, I can find x very easily because I already solved for x. X is equal to y plus 2, where x is equal to y is 2 plus 2, so x is 4. So since my x is defined, I have an x, I have a y. My actual solution is going to be the point 4, x comes first, 4, 2. So that's my solution, and since we're just starting, you want to make sure you check your answers. I want to plug it into each of the original just to make sure that it makes each of them true. Plugging in 4 for x, 2 for y. In the original, I have 4 plus 2 is equal to 6. This is true, 6 is equal to 6. Plugging into the second one, x is 4, y is 2. 4 minus 2 is equal to 2. That's true again, 2 is equal to 2, so since it makes both equations correct, our solution is 4, 2. X is 4, y is 2. Some examples may be given like this. You'll notice that my second equation is already solved for x. X is equal to y plus 19. So for here, I don't actually have to solve for any variable because it's already solved for. So now this x equals y plus 19, that's essentially also my star equation when I'm going to plug my y value into at the very end. So from here, it actually did one of the steps for me. So what I'm going to do is I'm going to take this expression y plus 19 and plug it in for x into the other equation. So using 1, I'm going to plug in, I'm going to substitute in y plus 19 for x, and then I'll solve for y. So we have 3 times x, I'm going to plug in the x there, minus 2y is equal to 42. Substituting in y plus 19 for x. I'm going to solve now by distributing and then just isolating x. So I have 3y plus 19 times 3. I can figure that out by saying, okay, 20 times 3 is 60 minus 3. So I have 57 minus 2y is equal to 42. From here, I'm going to subtract 57 minus 57 minus 57. 42 minus 57 is going to give me negative 15. 3y plus negative 2y is just y. So we have y is equal to negative 15. I'm going to plug that now into my special equation, which is my star. In this case, it's my second equation. So I'm left with x is equal to y plus 19. Instead of y, I'm going to put in negative 15. So x is equal to positive 4. So my equation is 4, negative 15. Again, I'll be plugging this into each of the original just to make sure that it is my actual solution. Plugging it into the first equation, 3x minus 2y, so 3 times 4 minus 2 times negative 15 is equal to 42. 3 times 4 is 12. Negative 2 times negative 15 is 30. 12 plus 30 equals 42. That's true. Second one, 4 is equal to negative 15 plus 19. This is also true. Negative 15 plus 19 is 4. So my solution is 4, negative 15. Working again, solving by substitution. Negative 3x plus 3y is equal to 4. Negative x plus y is equal to 3. So here I can actually know that I don't want to use my first equation, just because if I was to solve for one of the variables there, I would end up with a fraction. I would have to divide it by 3. Looking at the second equation, I noticed that if I was to solve for either of these variables, x or y, I wouldn't have any fractions because each of them has only a coefficient of 1 or negative 1. So either of them would be okay, but the easiest one to work with would be to solve for y, because when I move that x to the other side, it's going to become positive. And again, it's important to note that you don't always have to solve for x or always have to solve for y. It's just whichever one makes it easier to work with. And in this case, it's going to be using the second equation to solve for y. So doing that right now, I'm going to do 2. I'm going to solve for y. And you don't really have to indicate what you're solving for in each of these ones. I just do because I want to make sure I stay on track with what I'm trying to do. So I have negative x plus y is equal to 3. One thing I do suggest when you're working is to rewrite each of the equations first. So instead of trying to solve it in my head and then writing that, I'll actually rewrite each of the equations whenever I'm using it, just to make sure that I'm not making any little mistakes in signs or anything like that. So from here, solving for y, I will add x to both sides. So I have y is equal to x plus 3, or 3 plus x, doesn't matter. This becomes important to me. Starring that. Okay, now I'm going to plug in this x plus 3 into the other equation. So I'm plugging that into 1. So I'm rewriting it. Negative 3x plus 3y is equal to 4. I'm going to put this x plus 3 in for y. So I have negative 3x plus 3. Instead of y, I'm going to leave parentheses there for now, equals to 4. This y is going to become x plus 3. You'll notice I only have x. You want to only have one variable in your equation so that you can solve for it. So here I have negative 3x. Sorry, let me put that in black. Green. Negative 3x, distribute this, plus 3x plus 9 is equal to 4. Negative 3x plus 3x. This cancels each other out, right? So I'm left with 9 is equal to 4. So this is going to be one of the special cases. I already know it's either going to be infinitely many solutions or no solution, because my variable is gone. If your variable ever cancels itself out, that means that you cannot solve for that variable, obviously. So you're going to have one of these special cases. You can tell which special case it is by determining whether the resulting equation, which in this case is 9 equals to 4, you want to look at this and tell if it's true or false. So does 9 equal to 4? And obviously this is false, right? So since it is false, I can say that there is no solution. And since there is no solution, this system is inconsistent. Again, you have to indicate that it is inconsistent. So this is your actual answer that you'll be writing on the paper. For this last example using substitution, I can look at these right away and I say, okay, I already know I want to use my first equation and solve for y, just because it's the easiest to solve for. So rewriting it now. Solving for y, I'll move this 5x to the other side by adding it to both sides. So I'm left with 5x minus 3. This becomes special. I'm going to star that. I know I'm going to be substituting this expression for y, since it's equal to y, in the other equation. So now using my second equation, I'm going to plug this in. Negative 5x plus y is equal to negative 3. Just going to sub in 4y there. Negative 5x plus 5x minus 3 is equal to negative 3. So here I have, whenever you use addition, it doesn't change any sign. So I have negative 5x plus 5x minus 3 is equal to negative 3. Again, I can notice that negative 5x plus 5x, my x is canceled, my variable is gone. So now I'm looking at my resulting equation. Negative 3 is equal to negative 3. This is obviously true. So I can say that this is going to be, again, one of those special cases. And since it's true, I can say that there are infinitely many solutions. Oops. And then I will also have to indicate that this is dependent. Okay, so that's all for solving using substitution. I suggest trying this many times because this is one that does take quite a bit of practice in order to master. And in the next part, we'll go over the last way to solve systems of equations, which is using the addition-elimination method, also known as linear combination.